What specific problem does the paper address regarding the traditional understanding of layer normalization?
The paper addresses the traditional understanding of layer normalization, LayerNorm, by highlighting its often overlooked global effects on hidden vectors and the concept of irreversibility. It critiques the conventional view that merely standardizes each vector by subtracting the mean and dividing by the standard deviation, arguing that this process irreversibly discards information along the uniform vector, which may not be insignificant as previously assumed. The authors introduce a novel geometric interpretation of LayerNorm, demonstrating that it effectively removes the projection of a vector along the uniform vector, leading to a standardized vector that is orthogonal to it. Furthermore, the paper contrasts LayerNorm with RMSNorm, showing that the latter does not remove this component and still achieves effective hidden representations. This exploration challenges the adequacy of the traditional definition and suggests that the mean subtraction step in LayerNorm may be redundant, thus prompting a reevaluation of its necessity in model training.
How does the proposed method or algorithm work? Illustrate step by step, focusing on the transformation process of a vector during LayerNorm.
The proposed method of LayerNorm operates through a three-step transformation process of a vector. First, it removes the component of the vector along the uniform vector, bold symbol 1 equals 1 1 1 L dots caret T, which represents the mean of the vector's components. This step effectively discards information that may not be significant, leading to a new vector that is orthogonal to the uniform vector. Second, the resultant vector is normalized, ensuring that it has a norm of sqrt_d, where d is the dimensionality of the vector space. Finally, the normalized vector is scaled by sqrt_d, completing the transformation. This process not only stabilizes the hidden representations, but also orients them properly within the representation space, as demonstrated in the paper.
Can you provide a simple yet illustrative example demonstrating the inner workings of LayerNorm and how it compares to RMSNorm?
Layer normalization, LayerNorm, operates by first removing the mean of the hidden vector, effectively discarding the component along the uniform vector, which is a vector of ones. This process can be illustrated with a hidden vector, x equals 2, 4, 6. The mean is calculated as mu equals frac 2 plus 4 plus 6, 3 equals 4, and the standardized vector becomes y equals frac 2 to 4, sigma frac 4 to 4, sigma frac 6 to 4 sigma, where sigma is the standard deviation. In contrast, RMSNorm skips the mean subtraction step, directly normalizing the vector without removing the component along the uniform vector, thus retaining more information. For the same vector, x, RMSNorm would simply scale it by its norm, preserving its original structure while still ensuring stability in the representation space. This comparison highlights that while LayerNorm may lead to loss of information along the uniform vector, RMSNorm maintains this information, allowing models like Llama to produce representations orthogonal to the uniform vector.
What are the theoretical or practical benefits of using the new interpretation of LayerNorm as proposed by the authors?
The authors propose a novel interpretation of LayerNorm that offers several theoretical and practical benefits. Theoretically, this interpretation elucidates the geometric transformation of hidden vectors in representation space, specifically highlighting how LayerNorm removes the component along the uniform vector, which is deemed unimportant. This leads to the introduction of the irreversibility property, indicating that information lost during LayerNorm cannot be recovered, a concept not previously discussed in the literature. Practically, the findings suggest that the removal of the uniform vector component is redundant, as models trained with RMSNorm, which does not perform this step, still produce effective hidden representations orthogonal to the uniform vector. This insight supports the argument for using RMSNorm over LayerNorm, potentially leading to more efficient training and better model performance in large language models.
How was the method validated or tested in the experiments? Describe the experimental design, datasets used, and the metrics for evaluating the performance of LayerNorm and RMSNorm.
The method was validated through experiments involving 7 decoder-only large language models, LLMs, categorized into small and medium-sized groups, including models like GPT-2XL and Llama 3-8B. The dataset consisted of 1 million tokens sourced from Wikipedia articles, which were processed to capture hidden representations before and after each normalization layer across all model layers. The evaluation metrics included the L2 norm to measure the magnitude of hidden vectors and cosine similarity to assess orientation changes induced by normalization. The experiments specifically compared the effects of LayerNorm and RMSNorm on the hidden representations, highlighting the differences in their operations, particularly the mean vector subtraction in LayerNorm. The results demonstrated how both normalization methods stabilized the growing norms of hidden vectors, with LayerNorm significantly reducing the variance of these norms across different models.
What results were achieved with this new interpretation of LayerNorm, and how do these results support the author's claims about its superiority or limitations compared to RMSNorm?
The new interpretation of LayerNorm presented in the paper reveals that it irreversibly removes the component of a hidden vector along the uniform vector, which may not be significant for model performance. This leads to the conclusion that the information lost during LayerNorm cannot be recovered, contrasting with BatchNorm's reversible nature. The authors empirically demonstrate that models using RMSNorm, which does not discard the uniform vector component, produce hidden representations that are orthogonal to the uniform vector, suggesting that the removal step in LayerNorm is redundant. Additionally, the experiments show that LayerNorm effectively stabilizes the growing norms of hidden vectors in large language models, LLMs, but the authors argue that RMSNorm achieves similar performance without the drawbacks of irreversibility. These findings support the author's claim that RMSNorm may be a superior alternative to LayerNorm, as it retains more information while still stabilizing the model's hidden representations.